Okay, I'm starting the recording. So we're still missing our roll sheet. Did anyone looking for that person? He's now curiously missing. The case is taking on new dimensions. Well, I have another roll sheet, so we'll wait for some more people to show up. So remind me to pass that out, though. Okay, and we'll see if we can find the other one. Otherwise, I'm not going to be deterred, though. So we're going to continue to collect the roll. So I did a bad thing here and posted another homework assignment, all right, for you guys. So I hoping to collect homework 2, but now I haven't. I'm not slacking here. I've been working on the solutions yesterday to homework 1, so I need to grade those. But try to post the solutions. Of course, it takes me a little while to write out the solutions because I have to try to add sufficient detail to make the solutions clear, and that's challenging for these sorts of often for these sorts of problems. But I am getting to that, and since we have a test coming up a couple weeks from today, we do need to have a test review sheet, and so I have to make that out as well, right? So I've got a lot of tasks for the class. I have to kind of project where we're going to be by the time of the test, but we're making actually pretty good progress compared to what I was hoping. We'll see how fast this new material goes. So I'd like to talk about homework 2 next week. So try to prepare that, okay, so that we can discuss it next week and hopefully submit it, right? But I want to have a chance to make sure everyone can ask questions. We can talk about the problems before we actually submit it. And then we've got this new homework. Now, this is largely problems from the book, from chapter 2 in the book. We're working right at the beginning of chapter 2 in the book, and actually many of the examples that I'm doing in class here are from the book. So there are several problems from listed there from chapter 2 in the text. I don't know if there's a way for me to make that bigger, is there? Here? Okay. So there are several problems there from chapter 2 in the text. Now, that looks like a lot, but and some of those problems indeed they can be challenging, but the good thing about these problems is the answer is just typically a number. I mean, it's not like there's not any really show me problems in there, okay? But that doesn't mean they don't require thought, all right? So they are going to require some analysis, and they're sometimes tricky questions. They're good questions, but they're kind of puzzle questions. That's just the nature of combinatorics questions. So. But at least you don't have to write a lot of explanation necessarily with your answers. But again, try to avoid as much as possible, right? Looking for the answers, elsewhere. If you just write down the answer, but you don't understand how the answer came about, well, then of course that's not going to serve you well for a test, right? But now there are some. I did add some show me problems here. And there's one. We talked about this 180-degree rotation strategy for Gridmaster. That's the game in that we were showing in the notes, and I mentioned this strategy last time. So I wanted you to think more about why that is a winning strategy for player 2. If you can't remember that strategy, I'll remind you. You can ask me, and I'll remind you there. And then a couple of combinatorial geometry problems, just to have, because we talked about geometry is an important source of problems in combinatorics, so I wrote down some problems here for you. But these really don't require, they're not really, again, show me problems. They're counting problems, but they're fun counting problems. See if you can think about the answers to those. One of these, this is a famous problem from the internet, so you may have seen this on the internet. Okay, I generalized it a little bit from the version that's the version that you typically see on the internet. Okay, all right. So if you're having trouble understanding the understanding the description, because I didn't draw a picture here. Here I drew a picture, but there I did not. So if you're having trouble understanding the description of the problem, be sure to ask me about it. It's a pretty easy picture to draw from the description, but if you're having if that's confusing, ask me. And then remember what it means to draw lines in general position, right? That was we talked about that in the one combinatorial geometry example that we gave in the notes. Remember, general position means not parallel and not more than two lines intersect in a given point. Okay. All right. So that's a question about lines in general position, but not the same question that we answered in the notes. Okay. All right. So something else to work on there after homework 2. But homework 2 comes first. We're going to talk about these kinds of problems today and next time. And so I think after today's lecture, you'll get a better feel for, maybe not completely all of those problems, but a better feel for how you can go about attacking those, okay? Because that's exactly what we're talking about. These are all straightforward. Here's a description of a set. How many items are in this set? Okay, I think there may be one or two, more thought-type questions in there, but mostly that's what they are. Okay. All right. So, well, there it is. So, do y'all have any questions that y'all want to ask about things so far? Okay. Have y'all been trying homework 2 yet? Working on it a little bit? Okay. All right. So Monday at least try to spend some time with it between now and Monday so that you can ask questions about if there's really tough problems in there. I think those problems are a little bit more straightforward though than I think I mentioned this last time, a little bit more straightforward than the homework 1 problems. Okay. Maybe. I think. All right. Except maybe the last one. Maybe I'm fooling myself. Maybe I'm just I looked at them so much that that made them seem simpler than they first appear. Okay. All right. So we're going to go back and start talking about the notes. So I still don't have the missing roll. Anybody have the roll in their notes? Y'all aren't looking through your notes. So if you already looked through your notes, don't have the roll anywhere in your hidden away in your notes. Do you remember passing the roll on last time to somebody else so you weren't the last person who had it there? Okay. If you're the thief and you don't want to admit it, you can just quietly lay it somewhere, right? Just have it show up in class again mysteriously. Okay. All right. All right. So we were working on variations on this problem last time, and some of them we had already answered, but we have a few more. But I wanted to go back and we're going to revisit. Well, this is a very simple problem. And so, but we're going to revisit this problem again today using a slightly different technique, okay, to answer it. Not that it's hard to answer, okay, but we're going to apply a different technique kind of rigorously to this particular problem again. So remember, we were discussing the class, right? And we know that we can partition the class, the whole class, according to the major of students in the class, right? So I had done that. I had mentioned, right, that there were 12 math majors and some math teaching majors and some computer science majors and some data science majors. We weren't thinking about double majors. And then one philosophy major in the class, right? And now we're going to ask some simple answer some simple questions about the class. The very first thing is how many students are there on the class roll, right? Okay, and so that's a trivial question, right? That's really more of an arithmetic question than really a combinatorics question. Except we wanted to analyze that according to our the various theorems, right, that we had learned for counting, okay? And so what we want to do is form a model that we could use to answer, a set model that we could use to answer this question, right? So we did that by just mentioning that, these various subsets, right, of students that correspond to the different majors, right, they form a partition of the entire class, right? Because the union of all of those sets of majors, right? We gave each one of these subsets a name, right? The union of all of those, indeed, is the class, correct? And so that forms the entire class, right? When you take the union of all of those major specific subsets, right? And they're, because we're not allowing for double majors, then the subsets do not overlap, right? Okay, so those sets M, T, C, D, and P, right? That's a partition of the class, correct? Right? And so we know then that we can find the cardinality of the entire class, right? Just by adding up the cardinalities of the parts of the partition, right? Remember the subsets that form the parts, that form the items in the partition, right? The subsets in the partition, those are called the parts of the partition, right? And so this is really just, I think that was Theorem 1, correct, in our notes, right? And so we're doing exactly like an elementary school student would intuitively do, right? Just adding up the different types of majors, right? And of course that gives us the size of the class, right? So intuitively you know to do this, but there's actually a theorem, right, that backs up your intuitive knowledge, right? And then we also, just to give us a chance to apply our other theorems, right, that we had written down for counting, we asked this simple question: how many non-computationally intensive majors are there in the class? And we said, well, you know, there's really multiple ways of answering that question. Again, that's a simple question, right? So it's easy to answer without trying to apply theory to it, right? But just to get a practice with using our theorems, we did that. So let's see, what did we do here? We said, let's let A be the union of these two subsets, correct? Right, that was the, what were those? The data science majors, and that's the computer science majors. So the union of those two parts of the partition, right, that's going to be the set of computationally intensive majors. And so the non-computationally intensive majors, right, is going to be the complement in the class, right, is going to be the complement of the set of computationally intensive majors. So the class plays the role of the universal set, right, for the purposes of forming the complement. And then, of course, you know, we have this, theorem, right, that the size of the complement of a set, right, is just the cardinality of the universal set minus the size of the set itself, right? Okay, and the size of the set itself is going to be just the sum of the cardinalities, right? Okay, of the two sets that we put together to form the set of computationally intensive majors. And again, that's just another one of our theorems, and that's because these two sets do not overlap, correct? By the way, what is that theorem called that says the size of A here is going to be the size of D plus C? It's actually really just Theorem 1 stated, kind of restated in a simpler way, right? But it has a name, okay? So if you form a set as the union of two disjoint sets, right? Okay, then which is what we're doing here. Then the size of the union set, right, is going to be the sum of the cardinalities of the two subsets, correct? That theorem has a name. Remember what that was called? It has a long name. The theorem is the name of the theorem is almost longer than the statement of the theorem. Yeah, that's inclusion, exclusion, right? So it's important to remember that name because we're going to come revisit that theorem a couple more times, right? Okay, so that's why I'm just sort of dwelling on it there. It's a very simple theorem, okay? But and you've probably used it since, who knows, right? Okay, since the time you learned how to count, you used it probably just intuitively, right? But it has a name because we're going to come back and revisit that. So that's inclusion, exclusion, and then our other theorem, which doesn't have a name, is just a theorem about how to, count the complement of a set, right? Okay, so it's just the size of the universal set minus the size of the set that you use to form the complement, correct? So we ended up here with, in this case, the answer is almost the least interesting part of the question, right? 15, correct? Non-computationally intensive majors. And then finally now, the last question that we're looking at, and I could tell from your expressions that, well, you were either tired because it was the end of the class, or this one was a little bit different to you, okay? So we asked this question. So if we want to pick a team of size 5, right, that represents every major in the class, okay, so we're going to build a team from the class to send to some competition, and we want every major represented on the team, right? So we want a diverse team. Then how many such teams are possible, right? Okay, so so we have to rely on, I think, the last theorem that we introduced here, and that's the theorem about the size of cross products, because we can use a cross product here as the model for the set of teams from the class, okay? All right, what was that cross product? Well, that was pretty easy, okay? It was just the subsets of each of the different types of majors, right? And then we formed the cross product of that. And we said, oh, that set is a model for the set of teams that we can form from the class, okay? All right? So when I say that one set, so I don't think I defined this in the notes last time, and so I went back and added a little bit to my notes, okay? So to make this just a little bit more precise, okay? And again, it seems like I'm just, beating the horse here, all right? And I am, but I kind of have a larger goal, all right? So E here is the set of teams. That's the set that we want to count, okay? So that's the set that's mentioned in the problem that we're trying to count. But to count that, what we're going to do is we're going to do it indirectly, right? We're not going to actually form that big set of teams, right? Because that involves a bunch of people and so forth, right? Okay, so that's not a set that you can actually physically create, right, and look at, all right? But we're going to build a model for the set that we can actually think about, okay, so that we can sort of create and examine a little bit more closely, all right? So here's the set of teams that we want to count, but here's my model for the set. So I called that E prime, all right? And that's going to be my cross product of these subsets, all right? The set that corresponds to each of the majors, okay? Now, when you form a cross product, of course, what do cross products consist of? So what are the things that are in a cross product set? What are those called? Tuples, right. And remember, a tuple is just a generalization of an ordered pair, right? Okay. A tuple is just a list of elements, all right? But the elements, the things that you are listing, they have an order, okay? For those that are computer science majors, lists are ordered sets, right? Okay? So a tuple is just a list of things, all right? In this case, our tuples are going to be 5 tuples because each of the tuples is going to have 5 elements in it, 5 coordinates in it, so to speak, correct? Okay, 1 from each one item in the tuple, right? 1 coordinate in the tuple is going to be an element of each of these sets, correct? Well, our theorem says we know how to find, right, the size of a cross product, because it's just going to be the product of the cardinalities of the sets used to form the cross product, right? So to count E prime, that's easy, right? You just have to know the cardinality of M multiplied by the cardinality of T multiplied by the cardinality of C, D, and then P, multiply those all together, and that turns out to be 144. So that's how many tuples we have in this cross product. Therefore, that's how many teams that we can form from the class, right? So when I say that one set is a model for another, okay, that means different things in different situations. But in this class, when you say that one set is a model for another, you mean it's just it's a very simple relationship between the two. What's the relationship between a set and its model? Why do I say that one set is a model for the other? Because we're hoping they have the same what? No. Well, in a sense, yes, kind of. But in combinatorics, when I say structure, it's that means something very primitive. Okay. When I say they have the same structure, what I'm really saying is what? They have the same what? They have the same cardinality, right? They have the same cardinality. Or, in other words, there is a one-to-one correspondence between the set and its model, okay? Right? You can match every item in the first set with an item in the second set and vice versa, okay? So there's a one-to-one relationship that you can form between the elements of a set and the elements of its model, all right? Now, in this case, I was a little bit vague about what these sets M, T, C, D, and P are, okay? I think I said exactly M is the set of math majors, T is the set of, teaching majors, right? So that's really a set of people, okay? So when you form a cross product here, you really get a tuple of people, all right? Okay, I mean, that's fine. That's great, and it works fine to solve the problem. But I want to point out we can be a little bit more abstract about what M and T and C are, okay? We don't have to exactly think of M as being a set of people, okay? We can think of it as a set of something else as long as M, whatever I choose for M, as long as M has what property? More than it's not empty.
Cardinality of 12.
You must have cardinality of 12. That's right. Okay, yeah. So you can let your set M really be, you don't have to think of it as being exactly the set of math majors. I mean, exactly as a set of people. You can really let M be a set of more convenient objects, okay, since people are a little bit hard to sometimes work with, right? Okay. I'm not talking about personality-wise, but just, you know, the logistics of it, all right? But you can let M be a set of things that are easy for you to manipulate, easier for you to deal with, as long as M has 12 elements in it, okay? Meaning that M must be what? Help me here. The word I'm looking for begins with M. Model for what? The set of math students, that's right, okay? But what does it mean for a set to be a model for the set of math students? Has the same cardinality, that's what we just said, right? So you can really let M be any set as long as it's got 12 elements in it. What's an easy set for you to pick out that has 12 elements in it? The positive integers 1 to 12, sure, right. That's the first one you're going to think of, right? So instead of thinking of M as being a set of students, you can think of M as being a set of numbers, okay? And it can be the integer segment here of the first 12 integers, okay? Remember, that's my notation for the set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, which we are pretty certain, I don't think we're going to fight about this, has 12 elements in it, correct? Okay? Yes, all right. So M can be this set, and then likewise, see, you can let these other sets be sets of numbers. What was T there? It would have to be what? 2, right? Okay? And have to help me here. C could be 3, and D is 2, I think. Is that right? And finally, P is kind of boring there, but it's 1. All right. So there. Okay. So see, those can be your choices for M, T, C, D, and P. Right. So those are not really sets of students, but they might as well be sets of students, right? This is a model for the set of students. This is a model for the set of math majors. This is a model for the set of teaching majors. Then, when you form, Kaylee, see, when you form this cross product, it's a lot more clear what those elements of the cross product look like, right? Can you just show me what, if this is my choice for those 5 sets, can you just show me an element in that cross product? Just as a for instance. Remember, it's going to be a tuple, right? It's going to be a tuple with 5 coordinates. So just make up a tuple with 5 coordinates, right? But remember, the coordinates have to come from these sets, correct? Right? So, so the first coordinate comes from this set. What is something in this set? The number 1, sure, right. Or you could have picked 2 or 3 or 4 up to 12, correct? Right, yeah. All right, so 1 there, right? Now, second coordinate. I got to pick something from this set. 2, sure, right? Or you could have picked 1 again, right? Okay, 2. And then so forth there, Kaylee, so give me another one there. 3, right? What about from D? 2 again. And what about from P? Well, you don't have many choices there, right? 1, right? Okay. So that's just a random tuple that happens to live in that cross product, right? But how many, of course, tuples are in that cross product? We could have created how many of these things? 144, right? So if I'd spent some time and thought about it, I could have written down 144 different tuples, right? That's how many there are. Now, the question is, what team does that tuple represent? See, because remember, this set has to be a model for this one. So there has to be a one-to-one correspondence between this tuple and a team. But what team would that be? So what team could that possibly represent? Remember, teams are sets of what? What things go into teams? People, right, okay. All right, so what team of people from our class does that tuple correspond to? See, there has to be a one-to-one correspondence between these two sets, right? So this would be what? On our team, we put math major who? Math major 1, that's right, okay? So, see, someone we had to label as math major 1, correct, okay? And someone was going to be labeled math major 2, someone was going to be named math major 3 up to someone is math major 12, correct? Right, okay? So, see, we have to turn our, this is what everybody hates, right? We have to turn our people into numbers, you see, okay? Right, okay? See, everybody complains, I'm just a number, right? Nobody really appreciates me. Well, it's true in this case, right? So we're going to turn our math majors into numbers. They'll be math major 1, math major 2, up to math major 12. That has to be agreed on, by the way, beforehand, okay, right? But that has been, at least ideally, that's been agreed on beforehand because remember, you already said, oh, this is a model for my math majors, so I already have I've already established, correct? I've already established a one-to-one correspondence between this set and my set of math majors, correct? Right? Okay. So you have already ideally said someone is going to be math major 1, someone is going to be math major 2, someone's going to be math major 3. Doesn't matter how you do that, Eduardo. Okay. You can do it in alphabetical order if you like. All right. Just to establish that correspondence. Okay. Right. So this team consists of math major 1. What is it? Teaching major 2, whoever that is, computer science major 3, data science major 2, and yeah, this we know. Okay, right, all right. We know who's going to be the philosophy major, right? Because there's only one of those, correct, right? So you see what's really happened here under the hood is there really is some math going on here, okay? We're setting up correspondences, we're building sets, okay, and then using our theorems, right, to count these sets, okay? So now, all of that is kind of, but I said it's under the hood, right? All of that's kind of, when you're counting the set, all of that's kind of going on in your mind, but it's kind of subconscious to you, right? Okay, your intuition is sort of carrying out all these processes, but you're not thinking about them explicitly, right? But if we sort of analyze carefully what we're doing implicitly, this is really what's happening, all right? At some sort of molecular or some atomic level, right, in your brain, okay? This is what's going on, okay? All right. Well, let's try another one then. See, now that we've got our model set up, right, then we're really in great shape to help us with the counting carefully from now on. So, but we may need some more models here. Okay, so how many teams are there that include Dalton or Kaylee, both of whom are math majors? Okay, so both of whom are math majors. So we want teams that include Dalton or Kaylee, right? Both of whom are math majors. All right, so you can probably, I think, again, intuitively figure this out, okay? but let's try to write down a solution involving sets. All right. So again, you're going to find this kind of painstaking and think maybe sometimes, oh, Dr. Waller is just making this more complicated. That needs to be, yeah, I am in a way, okay, making it more complicated. Maybe that it takes to answer the question, but that's so that when we answer more difficult questions, we're maybe better prepared to handle them, right? Okay, questions that do require some more careful thought or more careful analysis. All right, so teams that include either Dalton or Kaylee, both of whom are math majors. So we want to somehow build some sets, right? Okay, so that we can answer this. We can answer this question. All right. So, any ideas there? It's definitely a set of teams, right? So that may involve some cross products, right?
M is modeled by a smaller integer set.
Oh, so I see. So I see. So Dalton is suggesting let's just maybe use a similar model, okay, as before, but we'll just restrict M, okay, to what? Two options, right. Someone else was, you're raising their hand. Other people were asking me here also, right? What was your question?
Well, saying that, never mind, I answered.
Okay, right. So I think we're going to use largely, right, the same models that we had before, right? So T can be the same, correct? And I don't know if I need to write all of this down again. Down to, of course, P can be the same, right? But M, we're our first set, correct? We're going to use a smaller set than before. So let me call this M prime, which is restricted. So Dalton just suggested we restrict that to what? 2, right? Okay, because we want sets that include, right, either Kaylee or Dalton. They cannot both get included because they're both math majors, right? Okay, so it was always going to be the case that it would be, at most one of those on a team. But of course, some of our original teams don't have to include either one of them. Okay, so instead of using the set of all math majors, right, as a possible part, right, of our cross product to build the teams, we'll just restrict our set of math majors to 2 choices. So 1 and 2 there have to represent what? Just 2. See, M prime only has 2 elements in it, correct? So 1 and 2 have to represent what?
Kaylee,
Yeah, Kaylee and Dalton in some order that we have picked, right? Okay. What now?
Are you going to assign each one of them an element?
Yes, right.
Major 1.
Yeah, so now and this may be different than what I used before, right? Okay, so now in this situation, I don't know who Math Major 1 was before, who Math Major 2 was, but now I'm going to say Math Major 1 is Kaylee, Math Major 2 is Dalton, right? Okay, so another way of thinking of M prime, other than just as 2 integers, I guess we could think of them as just the names, right? So we could think of this as just these 2 words, right? Dalton, Kaylee, right? So those 2 strings of letters, right, that we call names, those we could also think of those as being M prime as well, okay? So I shouldn't write that M prime is both of those things, right? Okay, but we have a choice here. Really, any 2-element set, right, would work, right, for M prime, as long as it was clear to us, right, what the mapping between those 2 elements in the set were, and between Dalton and Kaylee, right, the people, Dalton and Kaylee. All right, so what do you want to call the set that we want to count here? T prime? No, E prime? No, I've already used E prime. Okay, so running out of things here. All right, what? S prime. M double prime or E double prime maybe. There you go. All right, I like that thinking. Okay, so E double prime here now would be what? Now M prime, right? Cross all of these other sets. I forgot what they were. So there's a C and a D and a P, right? And now very easy to count, right? The cardinality of E prime, right? So this is just 2, right? Times 2 times, what is it? 3 times 2 times 1, right? What is that product? 24. Okay, so we have 24 teams that include either Dalton or Cayley. Okay, nice. All right, now let me ask you guys this question. Do you think you could have counted that easily without going through this process? Could you have come up with that answer, or do you think that would have been a tough counting question, just based on your intuition and observation,
I think it would have taken
and maybe exhausting possibilities, which is often how we count.
I would have used something similar. It was just like two choices.
Oh, I see. Yeah. All right. We're gonna get to. The scheme that you're using. We're gonna talk about today. Okay.
like
All right.
probability and statistics.
Exactly that. Oh, I see. Right. So we're gonna talk about that scheme that you may have seen introduced earlier. All right. Okay. That's gonna be our second big method for counting. Okay. All right. Someone else have a comment on that? So, think that would have been hard, Sean? Could you have? This is SEA. No, you're SHAW. Yeah, you're coming up here in a moment. All right, so you're in a question. SEA. Do you think you could have got through that? Second, Sean?
Calling me out.
Just asking you.
No.
You can always say, "Oh yeah, sure," right? And then.
Came in late.
Yeah. Okay. All right. Well, you can say I'm totally lost, so and that's fine too. Okay. All right. So now this one hopefully is easy. How many teams now include neither Dalton nor Cayley? It's not the inverse.
Yeah, but I mean like
The
universal
complement.
set.
The complement, right? Yeah, the term is complement. Okay. Yeah.
Universal
Yeah.
set.
I don't know if sets have inverses. That's a good question. Does that term apply to sets? But correspondences do, one-to-one correspondences do have inverses, okay? Not sure we're going to discuss those, though, all right? But what you're referring to is the set complement, okay? Right. So the teams that include neither Dalton nor Cayley, that's the complement of the teams that include either Dalton or Cayley. Complement in what's our universal set, though? What now? E prime, right, okay? Or similarly E, right, which is just the set of teams with people in it, all right? So, so let's see. So what we're looking for here is the complement, right, of E prime, correct? And, right, so how do we count that? According to our theorem about complements? That's going to be the universal set, right? Okay, its cardinality. So either E or E prime will work here as our universal set. Minus, and then what? That's right, the minus the size of the set that we're forming the complement from, right? Okay.
Cardinality of complements would be double prime there.
Yes, right. So I had different things on different sides of the equation there, right? So, all right. So, and now, so pretty simple, right? Because we counted this was what, 144, right? Minus this we counted as 24. So that's pretty obvious, right? 120 include neither Dalton nor Cayley. All right. So straightforward. All right. Now this question is very similar, but it has an important difference. All right. So. How many teams include either Eduardo or Sean? Now, we have to now figure out, though, what their majors are. So, Eduardo, what is your major? Math. Okay, so Eduardo is also a math major. So, if it turns out Sean is also a math major, then we're done, right? Because this will be equivalent to the prior problem, correct? But Sean is what? Data science. Okay, so that is... that's going to create a little bit of an issue here, all right? But let's go ahead and it is certainly similar to the prior example, right? Or, well, not exactly the prior example, right? But the one before that, right? So let's just try to attack it the same way, right? Okay, this is be sort of the student's approach, right, to the problem, right? These two, this problem and what is it? Yeah, E. Is it E? D look, so F and D look like there should be really the same problem, correct? So let's just try to answer it the same way. All right, so that means I've got to set up some new models here, right? So I want to restrict my let's see here. So M is just, oh yeah, I want to restrict M, right? So now we have another version of M, but that's pretty easy. What would be our new version of M? 1, right, because I'm just going to pick Eduardo, right? Okay, and then let's see, we go down here, right? So T is still what it was before, right? And C is still what it was before, but D is restricted, right, to just Sean, okay? And then P is still 1. So it looks like teams that include Eduardo are Sean. So we're going to go up to triple prime here, all right? Looks like those should be what? M double prime, cross T, cross C, right? Okay.
That should be D prime.
What now? Oh, D prime?
There's an issue with doing it like that, though.
Yeah, there's an issue with doing it like that, right? Okay.
You're not answering Eduardo or Sean, you're answering Eduardo and Sean.
That's right. Yeah, okay. Times what here? P, right. Okay.
That should be D prime in the line.
Oh, D prime?
Yeah, cross.
There we go. All right, so that's pretty easy to count, right? This set, right? What's that going to turn out to be? This is what? 1 times 2 times 3 times 1 times 1? Was that 6? Okay. So so we looks like the answer is 6, and then we go on. But Dalton's already said something is wrong here, right? This is not quite what we're looking for, right? What's wrong with this?
That's and Sean, not or Sean.
Right. So the tuples in this set, right? Because of the way we created these subsets, correct? Right. The tuples in this set have to always, in their first coordinate, have 1, right? And have to always, in the fourth coordinate, have 1, correct? Well, tuples that have 1 in them must include Eduardo, because Eduardo obviously is who we've assigned as being math major 1 in this case, right? And must also include Dalton, right? Okay. Sean, because the fourth coordinate has to be 1. Okay. So we do have teams here. Those 6 teams do include either. Those 6 teams do include either Eduardo or Sean, right? But we don't.
Some teams are only included in some teams.
Yeah, but if I replaced, so let's take one of the teams here out of our cross product, right? Okay. If I replaced on that team Eduardo by Dalton, that team still would include whom? Sean. That's either Eduardo or Sean, right? So that team should have been included in my set model, correct? Right? Or if I replaced Sean, kept Eduardo, right, but replaced Sean with another data science major. We have 2, correct? Right? I don't know who the other one is, but all right. So what is your name? Chad. So if we replaced Sean with Chad, that team also would include Eduardo, so it met the conditions of the problem, right? Okay, it's a valid team, therefore. We should have counted that one, but that's not going to be that's not going to be part of our set model, right? So of the one that we've created. So this set model is not, it's not right, okay? It's not a proper model for the question that's been answered here. Okay, so what do y'all suggest?
We have to have 3 different instances.
Yeah, Sean, number 2 there. Okay, yeah.
So, shouldn't we change it to replace the d prime with just d, and then add m prime times t times c times d prime times p, and then subtract what's up there?
Okay, so let's take it step by step. All right. So you're suggesting. Okay, the first thing you suggested was what? Keep all of this the same, except do what?
Change the d prime to just d.
So keep this except change the d prime to d.
Yes.
All right. So let's write down that set. This is a slightly different set, right? It's a little bit bigger set, actually. Correct? So we got to give that a name. So you want to start using numbers here now? E sub 4, okay, or something like that, right? Okay. All right. So what is that? What is that cross product model?
That cross product models all the teams that I believe Eduardo is on.
Ah, that's right. Yeah, exactly right. So this is all teams, including Eduardo, correct? Okay. Yeah. Spell that out in words. So this is all teams, including Eduardo.
Actually, it would including Eduardo, but it would include Eduardo and Sean, or for Sean.
Yeah, no. It could include both, right? Okay, but it also may not include Sean, correct? So when I give a description of it, the only thing I can really say for sure is all these teams include Eduardo, right? I'm certain of that, right? All these teams include Eduardo. Now, but we can also build a second set similar to this one, right?
Yes.
By doing what?
So we, instead of having m double prime,
So have M prime. Oh, M prime? No.
I'm not working with complete.
Okay, M is the set of all math majors. All right, yeah. So just M. Okay, right.
Then times t times c.
Yeah, times T times C times D prime times P here, right? There you go. And what is this?
That is all teams including Sean.
Ah, exactly. All teams including Sean.
But we need a third set.
We certainly do, right? Okay. But your third set, I think, is the big one, right? Isn't that the one you want? So isn't that E triple prime?
Yes.
Yeah. Okay. That was the original thing that that's the original name we were trying to give to this set, right? Okay. So how are you going to get E triple prime?
So wait, e triple prime?
Yeah, wasn't that our name? Wasn't that what we were?
Yeah.
Wasn't that what we were hoping for? Is the right thing?
Oh,
Okay.
Yeah. So to get e triple prime.
Oh, no. Let's keep this E triple prime. I'm sorry. Okay, because I'm going to use that again in just a moment.
Okay.
All right. So, all right, let's try E6. This is what we want, right? So, so in words, this is all teams with either, right? Is what you're hoping for. Forgot the names now. What is it, Eduardo or Sean, right? So this is what you're hoping will be your ultimate answer here, right? So you're thinking this is what?
This is e4 plus e5.
E4 union E5, right?
Yes.
Yeah.
And then
But why can we not stop there? So y'all have already figured out what the problem is, right? Why can we not stop there?
You're including a team with both of them.
That's right. Okay. Unfortunately, this set is a little bit too large, right? And when I say it's a little bit too large, the problem is you want to count E6, correct? So you would like to count the union of these two sets, right? Well, we have a theorem to do that, correct? We have a nice theorem to do that. Forgot what the number is, right? But it's the inclusion-exclusion theorem, right? So you're hoping that E6 is just E4 plus E5. But for inclusion-exclusion to work, these sets must be what? Disjoint. But they're not disjoint, correct? Okay? Those sets both include what? They include E triple prime, right? Okay, they include teams with both Eduardo. They both have teams with both Eduardo and Sean, right? So unfortunately, E triple prime is in there twice. Okay, so the sets are not destroyed. Do y'all see that? Okay, these sets overlap with teams that include both Eduardo and Sean. Okay, that team has that set of teams has teams that include both Eduardo and Sean. This set of teams have teams that include both Eduardo and Sean. All right. So how do we get rid of that?
You can adjust E5 with a small adjustment.
I have an easier way. Just do what?
You can just subtract E triple prime.
Oh, sure you can. Yeah, we're just going to do it right there. Yeah.
You also set up
That's right. Okay.
Should you put parentheses around that, or does it matter?
Actually, when I say I'm going to subtract it, Dalton's right. I'm being a little bit. This is really not quite correct. All right. But what I'm going to do there is still count E6 by subtracting it. So I can subtract it numerically, but if I write subtracting it out as a set, that's a little bit. I have to be careful about that, all right, because of the way sets work. So let's go ahead and build this set. And now this is not quite the set we want, right? Okay. Well, let's say that is the set we want, right? But this set is not quite the union of these two. No, I'm sorry. It is the union of these two sets. So this is still correct. But the counting is the problem. So when I count E6, I can take E4 and combine it with E5. That is okay. But what have I double counted? Yes, I've double counted E triple prime, right? Okay, so that we must subtract out. Because that was counted in both of these sets, all right? So that inclusion-exclusion theorem, this is a little bit more sophisticated version of that, right? Okay. Indeed, I could add these two cardinalities together to get the cardinality of E6, but that's a little bit too big, right? So I have to subtract off this set that was included in both E4 and E5, so it's not double counted. Yeah, Kaylee.
So, would it be easier to say E4 and E5 for E6? Because then it's only, no wait, I'm thinking backwards. Would it be easier to say E4 and then put E5 without the elements in E6, like in parentheses?
No.
So you don't have to put that to know that the cardinality is going to subtract E.
No, no, but it's because of the way sets work, a little bit different from arithmetic, right? When you take the union of two sets, right, you don't list, if you have elements that are in both sets, you don't list them twice, okay? You wouldn't list them twice, right? Okay? So the double counting is sort of accounted for when we take the union of the two sets, okay? So this is correct, all right? This is fine, all right? But it's the counting where things get iffy, all right? I'd like to just say, oh, E6 is the sum of these two cardinalities, but unfortunately, it's not, all right? Okay? Because the E triple prime, it gets counted twice, all right?
But just writing that for the set, we already know that the cardinality is going to subtract.
Right. Well, okay. Well, we're going to learn that soon. Okay. That's the second version of inclusion exclusion. All right. Which says if you take the union of two sets which are not disjoint, right? See, these sets are not disjoint. They overlap. Right. Okay. All right. Then you can count that union. You can count that union by adding up the cardinality of the two subsets, right? But then you have to subtract off the overlap, all right, which is what we did here.
We're using a theorem that we just haven't learned.
That's right. But it's kind of intuitive, right? Okay, I was hoping that y'all did in fact see that. Oh, I've counted this. I've counted E triple prime twice in here, right? Okay, so I'm going to end up with this is going to be too large. Yeah.
So it just be simpler just because E triple prime is the intersection.
It's the intersection. That's correct, right? Okay, and when we state the second version of inclusion exclusion, we'll call it the intersection, right? Oh, okay, all right. So, well, how many did that end up being? Did we ever count those?
It's
78? Okay. All right, so remember in your homeworks now, you're so lucky because all you have to write down is this, right? Okay. You're trying to get to this number. So you don't really have to go through the complicated explanation of how you get to that number, but make sure you understand how you get to that number, right? Okay, so that you can try that again. All right, let's try another problem. All right, so this is kind of like building a team, but well, you'll see a little bit what the difference is. So a gift basket of tropical fruit is going to be chosen from this collection of fruit. So you can choose from 3 mangoes, 7 durians, and 4 rambutans. So y'all can look those up if you're wondering about tropical fruits, okay? Most people know mangoes. These two might be a little bit unfamiliar to you, all right? So but those are real, okay? All right, so now, but we're going to put some conditions on here. So if the basket can contain any number of fruit, but of course, we want it to be, a real basket. So it's got to contain any number of fruit, at least 3, but it can go up to, I guess, all the way up to 14, right? Okay, because you could put everything in the basket that you have. I mean, this is what's available to you, right? Okay, but the basket has to have any number of fruit, but it doesn't have to be. You don't have to have one of each. That's not a requirement, okay? You just got to have 3 fruits in there. So it could be all mangoes, for instance, right? Okay. So how many different baskets are possible? All right, under those conditions, okay? So how in the world are we going to model this? Okay.
We have to make this first, like say M is mangoes, D is durians, R is that third thing, and just set the cardinality of.
Okay, so I would go for that. So you're but just as a start, because that's probably where I might. So you want to let M be what now here? 3. Okay. 7. All right. And R is going to be 4. Okay. I'm with that. And now what are you going to do with those? So our set of different baskets, do you want to call that B? So that's our a set of different baskets there. So what's going to be your model for this? By the way, what is, Kaylee, since you brought it up, what are these things modeling? Yeah, in words, what is M, what is M supposed to represent, right? What is it a model for? So I know what the set M is. It's 1, 2, 3. But what is that in words? What is that set modeling? Is that the set of mangoes? Oh, okay, so this is the set of mangoes. And that's the set of, durians. It's going to be hard to spell out here. Durians, and this is the set of rambutans. Probably pronouncing that wrong. It's probably rambutan or something like that. Okay. All right. So that seems to make sense. But all right. So now, how do you get a model for B? We can try something. It's obviously going to involve these sets, right? Okay, so M cross. All right, so that's what I was hoping you would say, something like this: M cross D cross R. All right, yeah. So what does this set? What does this set look like? So remember, this is a set of what? What are the things that are in that? Tuples, right. These happen to be tuples with how many coordinates in them? 3. You normally call a tuple with 3 coordinate a triple, right, okay? So these are sets of triples, all right? And so you want to list out some of the triples here? 1, 1, 1, okay, and then another one here, 3, 2, 2, maybe. Is that okay? Yeah, etc. Right? Yeah, 2, 2, 2. Right. So that's what B looks like, right? But now I have to. But now look. All right. So let me be careful here, right? Okay. The set we're trying to count is the set of baskets. So that's actually a set of baskets, all right, okay, which I cannot create because I don't have the fruits and I don't have a basket, right, okay? So I cannot physically deal with that set, okay? But this set I can deal with because it's just tuples of numbers, right? So I've already started writing down things in that set, correct? So this is not really the set that we're dealing with, right, that we're trying to count. But this is a, what is it again? Model for this set. So let's give this a different name, correct, okay, because this is the model for the actual set, right? Okay, this is a set of baskets and fruits. That's a set of tuples of numbers, right, okay? But is it a model? We want the two things to what? Have the same cardinality. In other words, we want there to be a one-to-one correspondence between this set and this set, okay? So if there's a one-to-one correspondence, when I write down something in this set, I should be able to tell you what basket that corresponds to, okay? So here's the basket 1, 1, 1. So what does that basket look like? I think the way you've described these sets, though, this would have to be what? That's mango 1, right? So we must have painted a 1 on that mango, right? This is what? Durian 1, and this is, rambutan 1, right? Okay. And this is what? Yeah, okay. And so forth. But look, are those really different baskets? Think about when you give this to someone, right? Okay. If you gave them this basket and you gave them this basket, they would not know the difference, right? Okay. To them, both baskets have what? 1 mango, 1 durian, and one rambutan, right? Okay. One often does not distinguish between different fruits, right? Okay. Different people are different, right? Okay. They have names and identities, but fruits are a little bit less exalted, and so usually one rambutan and another rambutan are just both what? They're just rambutans, right? Okay, yeah. All right. So there's not Tom the rambutan and Jerry the rambutan like there might be in a cartoon. Okay, it's just there is a rambutan there, right? Okay. So, see, I think we've already gone astray. All right, because we've overcounted somehow baskets, right? This model is. Or maybe we've undercounted, but there doesn't seem to be a correspondence, right, between this set and the actual set of baskets, because these two baskets, I think, are really the same basket. Okay, so, all right, so either, so maybe, we need to think differently here about the problem. Okay, so y'all see the issue here? The big issue that underlies this problem is what I just mentioned. You really can't distinguish one mango from another, okay? You've got three mangoes, they're all the same, all right? If those were three people, you could certainly distinguish them, right? So if you were making a team of three people, having person 1 on the team versus having person 3 on the team, that would be different, okay? Those are different persons. But having mango 1 and mango 3 in the basket, really no difference, right? Okay, in terms of mangoes. So, So really, what really does distinguish one basket from another? The number of fruits of each type, right? It's just the number of fruits of each type, right? Okay, that's what really distinguishes one basket from another. So I think these sets we've described incorrectly. The sets may be right, though, okay? But I think our description of the sets we could change, okay? Oh, I see. So, so we do have to change the sets here, right? Okay. So Dalton is suggesting, since what's really important is the number of fruits of each type, right, in the basket, let's let these sets represent not the mangoes themselves, right? Don't let M set be the actual mangoes, but the number of mangoes that are going to go in the basket, right? Okay. The number of mangoes in the basket. All right. So. See the difference there, right? So not the mangoes themselves, okay, but the number of mangoes. All right, so can I write all that down here? Number of mangoes. Oh, there you go. Okay, so number of durians and number of the rambutans. And so these integer segments, right? Yeah, well, let's worry about that later, okay? So these integer segments are not really quite the right set, correct, for each of these, right? Because we also need to account for the possibility that what? That's right, that we don't, because there's really no requirement that we add. We said the baskets don't have to be diverse, right? Okay. We might have 0 mangoes in the set. How am I going to write that down now? I think maybe we'll have to, this time we're going to have to list it out, right? So 0 to 9, right? And then for durians, 0 to 3. Okay, yeah. I'm thinking about the digits. So is that 7? Right, and what's the last one there? Rambutans. So how many of those are there? 4? We're going to have lots of problems where we're asking questions about forming numbers from digits, and of course we have digits 0 through 9, so that's what I was thinking about there for the mangoes. Okay. So instead of letting M, D, and R really be the mangoes themselves, right? We'll just think of that as being the number of mangoes that go into the basket. Now I think right? Okay, that we can still use this cross product though, and that will still give us these tuples, correct? Right? Okay, like this, except now we have some tuples that include 0, right? So what gift basket does that really correspond to now?
One mango, one cherry, one, just one of each fruit, basically.
One of each, right, okay. A perfectly good gift basket, right, okay, with just one of each. This one, of course, is what? A little bit bigger gift basket, right, okay. That's 3 durian, 2, I'm sorry, 3 mangoes, 2 rambutans, right, 2 durians, and then 2 rambutans, okay. So they get 7 fruits there altogether, okay. Oh, that's much nicer, all right. Almost the answer to the problem, right? How big is B prime here, right? Well, that's the easy part. So how many of these are there? 4, right? Okay. And 8 and 5, right? So what's that number? 160? Am I doing that right? 40 times 4, 160. Okay. So there's a big set of possible gift baskets, right? But we've overcounted, correct? Because we had some conditions on our gift baskets, right? Okay. So this is a little bit too large, so we need to subtract something off of B, correct? Okay. To actually, so we need to modify this model a little bit, right? Okay, because what now is included in
For example.
yeah, that's right. Okay, an empty basket, right? So that's not a very good gift, correct? Okay, but we also have gift baskets that include what?
One fruit or 2 fruit.
Yeah, one. That's right, or 1 or 2 fruits, right? Okay, and we need our gift baskets there to include 3 fruits, right? Okay, so this is not quite right. Okay, the set model that we're looking for. All right. Okay, this one doesn't quite match up with the set of, I should say here, valid gift baskets, right? Okay, this is the set of different gift baskets, but the set of valid gift baskets is going to be a little bit different, right? Okay, so how shall we describe that? Let's call that B prime now. So the set of valid baskets that meet these conditions, and how does that relate to B prime? So what do we have to take off of B prime here?
Anything with less than 3 fruits.
That's right. Okay. So subtract off here, right? Baskets with what?
Less than 3 fruits.
Baskets with less than 3 fruits, right? So how can I count B double prime then? That's my set of valid gift baskets there. It's going to be something like B prime, right? Okay. But what do I want to take off? All of these, correct? Okay. So if we can count the baskets with less than 3 fruits, right, we'll just subtract those off. Can y'all count baskets with less than 3 fruits? I think we can do that just by inspection. Okay. So how many baskets would have less than 3 fruits? Oh, so that was pretty fast there. Kaylee, how'd you come up with 10 so fast there?
I just wrote the combinations of the triples.
So describe some of those for us.
When they're all 0.
Yeah, that's right. So if you have a completely empty basket, right? Okay. Or you might have what?
There's 3 options for just one.
There's 3 options for 1 fruit, right? Okay. And then
Then there's 3 options for if there's one of 2 different kinds of fruits.
okay.
There's
Yeah.
3 options for when there's 2 of one fruit.
There you go. Okay, so there's just 10 of these, right? Baskets with less than 3 fruits in them, right? So that we can just figure out by inspection. So we'll just take that 10 right off of that there. So what does that give us there? Did we ever count these things now? What was B double prime? What was that, 160? Is that right? Minus 10. So it looks like 150. Ooh, wow. Okay. Fun. So many times now, we have to improvise a little bit, okay? Like in this problem, when we're dealing with the sets, right? You may come up with just sort of an initial set model. It may be the correct set model, but it may be a little bit too big, all right? And so you may have to modify it slightly. Here we had to modify it just by taking out these baskets that had too few fruit, right? Hopefully, now, when you have to modify your original model, the modifications will be pretty easy, like in this case, right? We were just able to, by inspection, count how many baskets had less than 2 fruits, right? So we just took out the invalid baskets, right, from that set of all the different baskets to get the set of valid baskets. What did we really use there? But it didn't sort of explicitly bring it out. What theorems were we really using? What theorem are we really using here? That's the complement, right? Okay, we're really using the complement theorem. But the complement theorem is based on inclusion, exclusion. So these are really the same theorem, all right? Just in a different form, okay? See, what we were saying is the set of valid baskets is the complement of the set of invalid baskets in the universal set being the set of different baskets, all right? So we really were using complement there. Okay, well, we've got some more variations on questions like this, all right? Okay, yay, all right, so we're done. So be working on homework 2, right? Okay, because we want to talk about that next week. Roll, phooey. All right, so everyone sign before you leave. Did my roll ever show up? Someone stole my... Sure. Okay. Now you're on the watch list now. All right. So so sign that please before you go. Sorry, I forgot that. And we'll attach it there. Thank you. Bye. Y'all have a great weekend. It's gonna be warm this weekend. It's not be cold like now.